Namaskar, my dear friends. Let us continue the discussion about GaNFET high efficiency DC-DC converter design. So, as we have already discussed the design and detail of this particular, uh, data sheet that we had already. So, you can see we were discussing in last class a 100-volt low IQ synchronous step down controller for GaNFET. Okay. Now we'll directly go into the design equations. So, as you can see, this is the particular complete design that we have, and we have like input capacitors. You can see we have 100 microfarad, two are there. Then we have options for 47 microfarads, we have 22 microfarad, then several 10 microfarads are there. We have 1 microfarad. Okay, so many 1 microfarads are there. Then we have 0.22 microfarads, and then we have zero point 0.1 and 1 nanofarad as well. Some extra 10 microfarad is also given for the benefit purpose, okay, later on. Why this many parallel capacitors are given is to reduce the ESR value. So equivalent series resistance will be reduced by putting lot of parallel capacitors. That's the one advantage. And by keeping so many capacitors, you are going to meet the input capacitance requirement. Okay, as well as your IRMS current that will be required. IRMS that I will calculate. So that much current will be required at the input. That's the reason it is put. Okay. So what we'll do is we'll just go ahead with design equation again, and then we will see the complete design. Okay. So let us start with one by one. So as you have already seen the design parameter, so this was the parameter that was there. Now coming back to the frequency setting. So frequency setting, as you can see, we have a 500 kilohertz. So 74 is coming. If you want, you can set it 1000 kilohertz. So that will be 37 kilo ohm. So this is how this will be keep on changing. Okay, and as you change the frequency of operation, what will happen? My inductor value will change. So as you go higher frequency, my inductor value will be lower. But since it is a 12 a 15 ampere rating, and it is very critical design, so we have kept our nominal frequency of operation, which is 500 kilohertz. Okay, so 500 kilohertz, around 2.5 microhenry or 3 microhenry will come up. Okay, coming back to the inductor selection. Okay, so in inductor selection, what we will do is we will calculate delta IL, that is going to be 30% of my current, so which was 15 ampere. So 15 into 30%, that is 4.5 ampere. So my total peak current will come up as 17.25 ampere. Okay, however, our trip current is 20.25 ampere, so we will make sure we are going to select an inductor with current rating more than this. Okay, so that's the understanding you should have. Otherwise there will be a problem later on, because while selecting an inductor, it is very difficult to meet the saturation current scenario. Coming back to current sense calculation. So current sense calculation, what is happening is V sense, you have to take it the minimum one. So 50 was there, so 45 to 55 it varies. So 45 millivolt I have taken, and I am calculating the current sense as 2.3 milliohms. So this is what I am going to calculate. Now if I try to increase a little bit higher side, what will happen is, if I take 2 milliohms, it will reach to 20.25 amperes. Okay, so if you want 2.2, then it will reach to 18 amperes. So at what value you want to calculate, it's up to you. So if you want, you can go ahead for this design 1.8 milliohms, or otherwise 2 milliohms, both are fine. So I have taken 2 milliohms. Okay, and in that situation, we are going to calculate an RC filter based on the equivalent series inductance of this particular current sense resistor. So in that case, we are going to calculate RF as 500 ohm. So till this time, till this place, what we will do is we'll try to show you the circuit. Okay. So let us start the circuit. As you can see, we have frequency setting, which is 73.2 kilo ohm for 500 kilohertz. Okay. Then we have inductor value. So as you can see, inductor value is 3.3 microhenry that has been chosen. Two inductors I have given a place. One is from TDK, another one was from Worth Electronics. Actually, in the reference design also, they have tried choosing this kind of inductors from these two manufacturers. So that is also one of the reason we have also taken, because we don't want to take any chances from that. Okay. Then we have introduced an external catch diode kind of thing that is there from onsemi. You can see we have 2 milliohm current sense resistor, and this is the RC filter that I was talking to you. So 500 ohm it was there, but I have to put it 499 ohm. So 499 and this one. So this is how it is going to sense plus and sense minus pins. Okay. And this is the V out pin that is going to give you my 15 volt. All right. Coming back to the other parts, let us continue the design equation. So as you can see, we have output voltage settings. Output voltage setting VFB is 0.8 volt, right? And let us say we want to set my feedback current to be, like 50 microampere, because the recommendation is 10 microampere to 100 microampere current must be set, or otherwise more is also okay. Okay. So what we are doing is we are setting a nominal current of 50 microampere. In that case, RA1 is getting calculated as 16 kilo ohms. Okay. So around this or lower than this will be a better idea. If you reduce the current, then let's see, my RA1 is getting higher, right? So this is how you can vary your current passing through the feedback pin of this particular controller. If you want to keep 80 microampere, it will be 10. All right. So this is how I have set the value. So let us say we keep 50 microampere and we calculate as 16. So let us choose RA as 16.2 kilo ohm, and this is how we are getting RAB as 287.6. Okay. So these two values I have actually put in the schematic, and we are getting output voltage calculated as 15.00198. Okay. So this is how we have a very nice calculation. Okay. Coming back to the input capacitance, so input IRMS value is coming up as 9.8 ampere. So I have taken from the reference design directly. There is no need to calculate again. Output capacitor also in the same fashion. If you want, you can put it the values, and you will be able to find your C out. So that I'm not showing. I have deleted from here right now. However, I have taken from the reference design for that purpose as well. Coming back to the the junction temperature. So junction temperature, how much it will be? So if int VCC has the maximum capacity of 39 milliampere, okay, and if whole of the 39 ampere milliamperes is being used, and input voltage maximum is, let us say, 36 volt, okay, so in that case your IC junction temperature will reach to 105 degrees centigrade. So you have to make sure that my IC is actually working up to, I think I need to see that. So let me just open that. So junction temperature, working temperature for this IC is how much? Yeah, you can see we have 150 degrees centigrade. Okay, so it is fine. Okay, it is fine. Now coming back to the other part, so it is fine. So basically this particular current is, let's say you are consuming 10 milliampere, then in that case your junction temperature will reach to 60 degrees centigrade. So you have to make sure how much current you are consuming, and it depends on that what will be the junction temperature. So let me just give you a very nice idea. Let us say you are consuming int VCC 8 milliampere current, and your input voltage is actually 24 volt, which is not changing. So your junction temperature is just 53 degrees centigrade. So there is no need of heat sink as well. Okay. So this is how you make your choices better. All right. Now T on minimum, you have to make sure that T on minimum must be 40 nanoseconds. So our calculation also shows that. So we can see V out by V in maximum into FSW, that is 833 nanosecond. Okay. So if you try to switch it on little faster. So let me make my switching frequency as 2000 kilohertz, that is 2 megahertz. Okay, so let's see if what is T on. So T on is 208, that is also suitable still, so there is no problem at all. Okay, so I'll just put 500 only, not a problem. I just wanted to show it to you. Now output ripple, I have calculated. So you can see we have equivalent series resistance, let us say 3 milliohms, and delta IL was 4.5 ampere. So my V ripple is just coming up 13.5, right? And V ripple percentage is 0.9%. So you have regulation voltage less than 1%. So this is very, very good. Coming back to soft start timer setting. So let us say we've set to a 0.1 microfarad, then we are going to set it 6.67 millisecond. So if you want, you can set some other value as well. TSS, based on your recommendation, you set your value and you will be able to calculate your soft start timer. So let us say you want to set it 10 microsecond. In that case, you have to put 150 nanofarad, that is 0.15 microfarad. Okay. So this was all calculation about this particular, design. So if you wish to have this particular design sheet as well, or like calculation sheet as well, you can put a request and I shall be able to send it to you, right? Now let us see the design. So feedback voltage divider, you can see we have 287 plus 590 I have added extra, so that 287.6 it becomes and 16.2. So this is how we are having a VFB pin which is getting connected at this point. Okay. Then we have external voltage supply. So external voltage supply, I have done a V output connected directly so that it supplies for my int VCC, and this is how my efficiency will be increased. Why? Because my V output will be a regulated voltage which will not, hinder my input, internal voltage regulator. Okay, for int VCC. As recommended, the test pin must be grounded in the pin description. You can see, so it has been grounded, and ground pad is actually pin number 29 I have put, so that is grounded. Now power good, what I have done is I have just put it, pull up, and it is a test point. So I have put a test point here. Now let us set other points. So you can see we have drive under voltage lockout. So I have set it to 3.8 volts so that you have to put it to ground. If you want, you can remove complete part so that you can reduce your circuit complexity. However, it is always recommended from my point of view that keep these options so that if you want, you can always change this. Okay. But these are all I mean evaluation kit processes, so that's the reason you can avoid it. You can make a fixed decision of putting it ground and sort it directly. You don't have to put a resistor. Similar to that, DRV set also I have set it to int VCC 5. You can directly ground it. You don't have to put a resistor and all these things. So the reason why I'm explaining is so that you can make your a circuit in one go direct, right? There is no need of going for revisions and all. Okay. Since you are setting a 15 volt output, so VPRG can be left open. There is no need of putting resistors combination here. However, if there is a possibility to make a 5 volt output, then you have to ground it. Okay. If you want to make it 12 volt output, then you have to put it into VCC. So that's the reason these two series 0 ohm resistors has been put here, and you can set those things. And based on that, you don't need VFB resistors, and those can be removed from the things. The only change that will happen based on this voltage range changing is you have to change the inductor values. Okay. Now I limit setting, how much current limit you want to set. Those current limit can be set based on the either you can leave it open. So you can leave this point open. So it will be set to 50 millivolt. Otherwise 26 millivolt or 75 millivolt. So this is how, like, you can say 25, 50 and 75 millivolt it will be set based on the 0, open and high. Then we have a compensation. So compensation pin is connected with a 10 kilo ohm resistor and these two capacitors. Similar to that, we have dead time insertion. So dead time A and dead time B, zero insertion has been made. If you want, you can put a dead time for the switching on and switching off circuitry. So let us say how it happens is, let us say one of the switch is going switch off. So what do you want? Do you want to switch on the other IC after some time? So this will be considered as dead time, and that you can configure through adding a resistance between the pins and the ground. Okay. Otherwise, people, what do they want is they want to immediately start. In that case, what will happen is you have to put a zero a dead time. So zero dead time can be programmed by directly sorting these two int VCC pin. Okay. So this one you can directly sort it int VCC pin. Okay. So that's the reason I have put it 0 ohm. Coming back to soft start. So soft start timer I have put it. I am not tracking it, tracking the input. I am putting just soft start timer, which is 6.67 microsecond. Okay. Now coming back to next points, we have mode selection. So mode selection, what I have done is I have put a forced continuous mode. Okay, forced continuous mode. So this is how I have put it to the int VCC. If you want, you can put it in burst mode or something like that by putting it to ground as well. and I'm not using like PLL locked out and spread spectrum, so that's the reason I have grounded it. If you face any issues with EMIMC testing or something like that, you can enable this feature by pulling it up by making this 0 ohm resistor and remove this one. So this is how spread spectrum will be enabled, and you will be able to have a better EMI, like EMIMC responses. Coming back to the input voltage and run pin, so run pin I have directly like sorted it out, so that once you have voltage input available, your IC will start giving you output. There is no like control of switching on or switching off, something like that, through an enable pin, right, or under voltage lockout pin. There is no need of that. Then we have int VCC pin. So int VCC pin require like a 4.7 microfarad, but I have put 10 microfarad because this is a good like a value. And similar to that, we have driver set, driver VCC. So driver VCC I have put 0.1 microfarad. So 10 microfarad will be put near int VCC, and this 0.1 microfarad will be put near DR VCC. Okay. Coming back to the output side, so what I have done beautifully here is, as you can see very nicely, so we have top gate driver, so TZUP, okay, and yeah, I have put a TFET gate driver. So you can see TFET gate driver, two gate drivers, two MOSFETs I have utilized, EPC2088. So these two will be in parallel, Q1 and Q3. Okay, so Q1 and Q3 both will be in parallel, and this is how they will reduce the like a current stress, stress. And this is how I am going to make this little better. Similar to that, we have bottom side also two MOSFETs. So same two MOSFETs have been utilized. So these are bottom gate driver, and I have put a test points. If you want, you can always check it, like what is the value at this particular place. So these two resistors are here, and these two resistors are also here. If you want, you can reduce the cost by sorting directly to them. There is no need, but putting these resistors is always a good idea. We have bootstrap capacitor that is used as C42, that is 0.1 microfarad, that has been used through the SW pin. And we have Schottky diode as like, and this particular resistor, so that is my bootstrap VCC pin. So this was all about the complete design. Okay, now coming back to the output capacitance. So output capacitance, as you can see, I have put like 220 microfarad two times, and then we have 150 microfarad two times. So there are four capacitors here. We have 47 microfarad available for options. Then by putting 22 microfarad and 10 microfarad, I have tried reducing the ESR value at the output, and we have some filter capacitors as well. Okay. So if you want, you can always like connect more 10 like 10 microfarad capacitor, like two numbers more you can add. And similar to that, like you can increase 1 microfarad for more numbers, as well as 0.22 microfarad two more numbers. Okay, so this is how you can increase the capacitances to make it little better. Now to protect the output, what I have done is, since the output voltage is 15 volt, I don't want to take a chance. So I have put a 18 volt TVS diode here of like 30 kilowatt power, or if you want, you can use 15 kilowatt power as well from little fuse. Okay, so similar to that, we have output voltage connector. So these are two like stubs that are there from Worth Electronics. Like big stubs are there. We have through hole test points as well, which is there from Keystone, so that is there, and we have dots as well, so that can be utilized as a test point for the output voltage rating. Similar to that, we have input side as well. So coming back to the input side, we have input connectors and input test points are there. Okay, and we have here input side, I have put a protection. So I have put protection as like one varistor, DC varistor is there, and then we have one TVS diode as well for 43 volts. So since our voltage rating is 36 volt maximum, so I don't want it to like go as high as possible. So that's the reason I have limited it to 43 volt. So this is also like a 15 kilowatt power rating. So all right guys, this was all about like this particular GaNFET high efficiency DC-DC converter. And if you do have any like questions or any regarding the particular design that you wish to, so you can always reach out to me. And if there is a need of like a 5 volt regulator or 12 volt regulator for this particular like a DC-DC converter, this is very easy to do. You don't have to utilize this particular voltage divider circuit. All right. So, okay, all right. If you do have any question, please put down your questions in the comment box, and we shall be able to come up with proper, like solutions of any kinds of like challenges. Thank you so much.